And this PowerPoint is not up there because I was just working on it today. Well, it is. It's inside the math chapter, but I decided to split it back out. So it's going to be called input output, and I'll get it up there as soon as I can. Okay, so here we go.
Oh, that's not on. Yeah, you're. Unfortunately, I don't have eyes in the back of my head.
Even though some people think I do. So, I'll go ahead and go to the first slide. This is advanced PLC basic wiring or PLC wiring. And of course, our objective is coming up here is to define IO controls, identify DC syncing, DC sourcing, inputs, DC syncing, DC sourcing outputs. And then we have relay outputs and we have AC outputs, which will, inputs and outputs we'll look at. So these are some terms, guys, that don't need to know, because these are used throughout these manuals when you actually start looking at the manuals for the PLC. They talk about a field device. So what's a field device? From the PLC. That's basically it. Anything that's outside the PLC that connects to the PLC some way is referred to as a field device. Well, even the power supplies. The power supplies are considered. The power supply is considered to be outside the PLC, especially on a modular PLC. And this is called, so that's called a field device also. Syncing, what's syncing?
Syncing is put negative.
Yeah, so syncing devices use a negative common. Forcing devices use a positive common, right? Digital signals, these are represented by two voltage levels. In PLC, it's usually 24 volts DC. So we use 0 volts to usually represent a 0 and plus 24 around there. Every PLC, since they run in an industrial environment, there is a range that it will accept for a true and a range it will accept for a false. You can look at it in that. Analog, these signals that represent by continuously varying voltage is usually what?
0
to T. That's pretty common. We also have
4 to 20
I ain't got there yet. The next thing we use is what we refer to as current loop. Current loop does not use a voltage, it uses a current. Now, what's the advantage of using a current over a voltage? Well, that's not the real advantage.
Or set parameters on.
The problem when we get into industry, y'all shooting it. The problem when we get into industry is there's a lot of what we call EMI. You know what EMI stands for? Electromagnetic interference. EMI can change a voltage, but it's almost impossible for EMI to change a current. EMI cannot change the current because it's just a wave passing through a wire, right? You understand? So the big advantages of 20 milliamp and current loops is the distances are a lot further, because what we do on a 20 milliamp current loop is a really neat system. Is that the way we use what we call constant current sources. So it basically does away with resistance. As long as your output can give you the right voltage to cause the amount of current flow. So what happens to these outputs is they measure current. If they don't have 20 milliamps, it'll raise the output voltage to get what? 20 milliamps. But it can only raise it so far. So you can get out of the limits. Another big advantage of current loop over voltage is it's basically immune to EMI. There's almost impossible for me to have a wire and a magnetic field pass through that one wire and generate 20 milliamps. So a big advantage this is why you're going to run into a lot of current loops in the industry, is it's basically immune to electromagnetic interference, and that's the big advantage. But it makes no difference with the length of the wire either. So the length of the wire is ignored, but it only can do so much, right? You understand that?
Was you gonna say something?
One additional benefit to it is if you've got 0 milliamps, that tells you you've got an open circuit.
Yeah, and that's what, and that's the other reason, and that's one reason they never use 0 to represent a 0. They use a current, because it's almost impossible to me, it's impossible for EMI to generate a current. So they don't use 0. They use a current flow for a 0, and they use a current flow for a 1. Right? You understand? So that's your big disadvantage. And yeah, Thomas would say, if it don't have any current flow, you got a lot open. Of course, then you see the maximum output. But the biggest advantage of current loop, the biggest advantage is basically what? Impervious to electromagnetic. You'll run into that a lot, especially in instrument systems. NPN, these are solid state devices used to switch DC. These are going to be in our watch. NPN sensor, and a PNP is a solid state device used to switch DC. And these are going to be in our PNP sensor. An NPN sensor, we talked about that. What does it do? Syncs. A PNP sensor does what? Relay output modules. These are used as a relay output, allows current, either AC or DC. What's the biggest disadvantage of relay output? Yeah, they're electromechanical devices, right? So they have what? 2 ways they can fail. Are we okay on these terms? This is the basic layout of what we refer to as syncing and sorting. So notice on the first one, these are syncing. Okay, this is a syncing input. If the input is syncing, then your output is, your input device has to be what? Sourcing. Does that make sense? So here, notice the input is in the positive line of our DC. And then our module uses negative common. That makes sense? Okay. This would be output. This would be a syncing output. So notice the positive connects to the load, and then it uses the watt for a common. The PLC uses the negative for a common, right? I understand that. This is sourcing. So notice all they did on this diagram is just move the input down to what? Down to the negative side, right? And then the actual module is what? Use the positive common. So this is an input. This would be what we call a what? Sourcing input, which means your device itself has to be what? Syncing, right? You understand that? And this is the output side, right? So here the output, PLC uses the common. Uses the positive as the common. So your load uses the negative as the common, right? You understand that? So then this right here would be what? Sourcing output, syncing syncing load, right? I understand that. Did I say that right? Christine, what? Why don't we understand?
What determines which way it would be?
Well, what determines which way it would be is basically depending on your company and what PLC that you buy. Okay. Whether you buy a syncing PLC or a sourcing PLC. So we can buy PLCs in different configurations. You'll see over here, commonly over in the United States, and I'm not going to say you're never going to run into that. Normally what we use on the PLC is where you see the input over here and you use sourcing out. That's just what we use over here. If we're using it. Now understand, syncing and sourcing only comes into play when you're dealing with DC. period.
Right, okay.
That it has nothing to do with AC, because AC has no polarity. You understand that? So what we do on AC is we decide one of our sides is going to be neutral. We call it a neutral. And then your neutral is going to be common to everything. And then what electricians call the hot lead. That would be the ungrounded lead. So what happens, and I don't see I have a drawing set up on this thing. Oh, there it is. I didn't take it far enough. So the way houses are set up, or the way 120 volt or AC is set up, is we establish one lead that we refer to as hot. And then we have another lead that we refer to, I call it neutral. And then we have another lead that's referred to as ground. But what you find out is that back in your panel box, these two right here are wired together. And so neutral is our actual common for our AC. It's not our common for our circuit. Now, a National Electrical Code does not use the term hot and neutral. They do use ground. National Electrical calls this the ungrounded current carrying conductor. They call this the grounded current carrying conductor, and then they call this ground. So what's the difference between neutral and ground? This guy is supposed to carry current. This guy is not. If you get current flow in the ground, something is wrong. Right? You understand? So something is wrong. So what happens is something happens and this hot gets shorted up against the chassis of your refrigerator or something like that, it'll pop the breaker. Because that way your ground carries a current and your ground is not supposed to carry a current, right? You understand? So that's why they call it that. So you'll see when we get on these AC modules, they'll talk about neutral, hot, and then we always run a ground, right? That's not like a ship when you say run a ground. Run a ground. So what determines if we're sinking and what determines if we're sourcing depends on basically what your plant uses that you go to work with. That makes sense. Of course, if you're responsible for buying the PLC, you're going to determine what you want your input to be. You're going to determine what you want your output to be. That makes sense. That's your call. But normally you'll go into a situation where all this is going to be done for you. What you got to know is that, so one of the things that you've got to know or understand is that you got to know what your plant uses, right? You understand? Now on a modular PLC, it's pretty simple because when you look at the modules, they're going to be called what? Sinking or sourcing. I didn't bring my camera, but if you look at this input module right here, this input module says sinking and the output module says sourcing. It's written right on the module.
So it doesn't really have anything to do with what your outputs are or how much, none of that has to do.
I don't know what you're
As
asking.
far as whether it's the sinking of the source. Which one is sinking? What's on here? Or which?
Doesn't matter.
It does matter what
Okay,
what you use for common. So what we do if we're sourcing, and this is what this diagram here. So right here, this right here is our common. So this is our common to our PLC. This would be the common. This would be the common for our inputs. Now they're just showing one input. You understand? So if I was going to draw this in a ladder diagram, I was going to draw this one right here. This is going to be my minus DC. This is going to be my plus DC. And then I would come over here and my input switch would be right here. I'm sorry. This is plus. This is the first one. Yeah. I got it. Okay. So this would be plus DC on this side. Oops. And this would be minus DC on this side. So my push button would be right here. This would be the input to my PLC right there. and this would be right here. So this is the common for my, and if I wanted to do another input, I would take my other input, I would connect it right here, and then this would be to another input of my PLC. I would come over here and take another input, and then this would go to a different input of my PLC. Right. Right. We're dealing with this guy right here. We're dealing with syncing inputs. Okay. So this would be one of the inputs on my PLC, like input 0/1. This might be input 0/2, and this might be input 0/3. Okay. Now what's the common for all my inputs? Positive. What's the common for my PLC? Minus. Okay. So what we're saying, this is my common for my inputs. Now common, we get in to think that common is the return, but common don't have to be the return, right? You understand? Common is just a common connection point for a bunch of things. And so we get into this in PLCs where if my inputs use a positive common, then my modules have to use a negative common, right? You understand? If my inputs use a negative common, my PLC, my inputs are going to use a positive common. So I could just come up here real easy and just change these signs. So right here, this would be a sourcing input, but my module we call it a syncing because this is using the negative. Does that make sense? So all I'd have to do to change this over here would be what? Now, all they're doing is showing one input. They're not showing everything that's going on, but all I'd have to do is just come over here and do what? Change the signs. So if I come over here and make this a negative, then this guy right here's got to be a what? Positive. So here my inputs would be syncing and my outputs would be what? Sourcing. On the output side, we got to do the same thing, but over here, here's my output for my PLC over here. And here's my actual device I'm running. So let's put a light bulb up there. And then I'd come over here, I have another output port, and it might go to a relay, right? You understand? And then I might have another output port, and then this right here would go to maybe, I'll just put another relay. I was going to say a solenoid. We can do this. And this would be a solenoid. Understand? Well, if this is minus DC and this is plus DC, then my light bulb, my lights is the plus, so this would be source now, and this right here would be what? Sync. So my PLC is using a negative common, and my actual physical output devices are using a positive common. If I come up here and change this around, so I needed to change the sync and the source, right? If I come up here and change this polarity right here, and I make this plus and I make this minus, then my PLC would be sourcing, my loads would be syncing, right? Understand that? And what determines this on the modular PLC is if I'm using DC inputs or DC outputs, then this is predefined for me. If I buy a syncing input, then by George, it's wired sync. So when I plug it into that slot, it picks up on the wall. Negative, right? You understand? And then my PLC, the actual input itself, would be hooked up to the positive. So on this, we're using syncing inputs and sourcing outputs. So sourcing outputs means the PLC is referenced to what? Positive, and then what would I have to run to all my outputs? I'd have to run the negative. You have to run that. You don't have to do this. This is where? This is inside the PLC, right? Maybe. Go ahead. You gonna say something, Jay?
No, I just don't the card for the.
So when I go out and buy a fixed PLC, usually this is defined, except for Allen Bradley. Allen Bradley splits the inputs up and usually splits the outputs up, so you can configure in groups.
Yeah,
You can't
mess that up.
Huh?
You can't mess that up.
So we okay? So normally, normally your inputs are syncing and your outputs are sourcing if you're dealing with DC. So syncing and sourcing in AC, these are digital. Analog usually goes from where? 0 to 10 volts. There's no advantage to syncing or sourcing input. The only difference is how solid state sensors are connected. Right? Limit switches don't care if they're syncing or sourcing. Push buttons don't care if they're syncing and sourcing. The only time this really becomes critical is when you go to DC. Make sense? Very okay. DC inputs, some use only sourcing, some use only syncing, some allow the end user inside. Input module can be damaged if you connect them incorrectly. It should be obvious. If you connect a positive where you're supposed to have a negative or a negative where you're supposed to have a positive, they could be damaged. Now, most PLC understands that this gets out there to the user, so most of the time they'll put just like your remotes. If you put your batteries in backwards, usually the bulb just don't work. And actually, so they've got like a diode or something in there that blocks it if you put them in there backwards, right? You understand? So PLCs usually do that too. This is a typical input module. This is a little better than what the book did. What the book didn't put, they didn't put that resistor up there, which is required. This is what we call an optical coupler, also called an optical isolator. So we actually transfer information from the input over to the internal works of the PLC through a little integrated circuit. Now what's nice about that is that if you screw up, you're going to mess this thing up, but you're not going to burn up the internal works of your PLC, right? This is a typical AC module. This is called a bridge rectifier. So no matter which direction you flow, and what's so strange, and we're not going to explain why, current flows against the arrows. So if this is positive and this is negative, then the current would come through this resistor. It would go this way, come around, can't go that way because it flows against the arrow. It would come over here, go through my LED, come through here, go back through this, flows against the arrow, so it'd go this way and go back. Now if I swap my polarities, but it still gets confusing. If I swap my polarities, and so what did I have before? Okay, this would be minus and this would be plus. Then what would happen? Then it come up here, flows to this resistor, goes against the arrow, goes this way. And notice each time it goes through this the same direction, right? And it's looking for the other polarity. We're not swapping our hot and our neutral. Those are that fixed. All we're doing is swapping the sign on the next alternation, right? So all we're doing is just making, and this is AC, so AC is constantly doing one. We got to swap in polarity. The neutral will always be neutral, and the hot will always be what? Hot. So what's the difference between the neutral and the hot? This one's grounded. This one's not. There's no negative and positive. AC has no polarity. Right? You understand? Because why? Yeah. Our AC, we use 60 cycles. Our AC is changing polarities every 8.3333 milliseconds. Changing polarities, and they're just swapping. So it has no polarity. But we reference 1 to ground, but it carries current. This, I wanted to show y'all, this is a syncing system. And what you got to do right now is just look at these transistors that switches. That's all they do. They switch. But instead of you going up there and flipping the switch, they are what? They are electronically controlled. These switches are electronically controlled. So if this guy here closes, if I close this switch, this is going to connect this guy to what? To minus, right? If this guy right here closes, this is going to connect to what? It's what? Positive. That's what you got to do. You got to look at the switch. Now, these guys here have a standard color code.
So brown is the what? Brown is the plus, blue is the minus, and black is the what? It's dash and C. And that's the standard color code for a 3-wire system. So this one is going to connect the output to ground. So that would be what? Sinking, right? This is going to connect the output of the sensor to power to the plus. So this is going to be sourcing. So what happens is notice our common switches, right?
All the inputs. Are you okay? This is the MS Logic 1000. These are the ones that we have. And normally, what's nice about the RS Logic is they have a DC common. So they don't say source, they have what they call a DC common. And what do you think that means? Well, we don't, in DC, we don't use the term ground we almost never use ground. We call it the common. Because the common can be a what? It can be a plus, or it could be a minus, right? You understand? So what the 1000 gives you the ability to do, it gives you the ability to set them up at whatever you want. It don't say plus, it don't say minus, it says common. So what does that mean? Well, you can make, on the 1000, you can make the input sinking, or you can make the output sourcing. It depends on what you use for a what? For a common. Yeah, so right here it says common. So right now they say plus DC, but I could just as well do what? I mean, I could, so what they've done on these is they made these 3 inputs. So this thing is split up in these groups. They made these 4 inputs sinking. They've made these, all these what? Sources.
So that's, okay. And that can be, I don't want to, at the risk of sounding dumb, like I'm missing something altogether. Depending, do either one thinking or sourcing your inputs or outputs depending on how many you have. Is that what you're saying?
What Allen Bradley does is they assign it to groups. So I've never seen an Allen Bradley PLC that allows you to configure syncing or sourcing. It lets you configure all the inputs. Now normally it lets you when we go to the outputs on the 1100, you got access to every one of them because they're relay. If they're relay outputs, then you determine if they're syncing and sourcing. The Siemens that I've seen that uses relay outputs use this groups. They use groups. But Allen Bradley, when we go to the outputs, so here they got these set up for syncing. So they're putting so syncing inputs, but here's the positive, and the positive goes, this is my common for the positive, right? You understand that? So this is my positive right here. So my input devices are what? Sourcing. So this guy, when I come up here and set this up, notice what common over here, here's minus, and the minus runs to the DC common on this set. So what we've done is we've configured these inputs to be sourcing, and we've configured the outputs to be syncing. Who has to put that wire out there? You do. That's a wire. It's actually on the screws of the PLC. You have to jump that thing, right? You understand? So when you look at your PLC, like the 1100s, the 1000, you can see where they've got these things just jumped together. Well, they've got a wire coming over. I think they've got the output hooked up for sourcing. But they're using 120 volts DC, so they're a little bit. Okay, we okay? So notice what they got right here. So here's the common right here, right? You understand? This is going to all my inputs. So I'm jumping these wires down. I'm sorry. This is out on my actual physical devices themselves. And then what do on the DC common? They've got this hooked up to what? Plus. You see that? So they've got this set up for what? Sourcing inputs. They've got this one set up for syncing. That makes sense?
And then down here, they've got them swapped around. So notice here what they do is they take the positive and run it, they take the negative and run it to, this is my common for my switches. So here my inputs are what? Syncing, because that's the negative. I'm sorry, my devices are syncing. I need to get those straight. My input devices are syncing, right? So this guy right here has got to be what? Sourcing. That makes sense? And then of course they switch this around. But you don't have to do it like this. If you want both of them to be syncing, then you would do what? You would just take this minus and you would jump it right here too, right? You understand? If you wanted both of them to be sourcing, you do what? You just jump those together. Now our outputs are relay outputs. So these are the relay outputs. Now what's nice, and look what it says on here. AC or DC. Right. By the way, and this is what people don't understand, just about most of your, not all of them, but a lot of your PLCs that go AC, DC relay, they have a DC power supply built into the PLC, if it's not a modular PLC. But what does it say right here? It says I'm not supposed to use that power supply for my outputs. So that means you've got to have a secondary power supply, right? You understand that? Your PLC DC power supply is not designed to run outputs. It's designed to run inputs. It just don't provide enough current. So if I wanted to hook up, if I wanted to make all these outputs, and what's nice about this is every output is what? Either or. So you can put AC on these things. You can put DC. If you put DC, you decide if you're what? Syncing or sourcing. On our 1100s, they're using 120 volts AC. So that's why I told y'all to keep the covers on there. So what did they do? So what they did is we took, if this guy right here is syncing, right? You understand? Not syncing. So what we got is we got all these output devices out here that I'm going to connect up. Oops, wrong place, Rick. So the output would be right here. We'd have an output right there. I'm just going to put lights or coils. That doesn't make any difference. So what we do on AC, if this is AC, then what I would do is I would take L1 and I would run it where? Right here. I would run it right there, right? I'd run it right there. I would run it there. I would jump it to here. I would jump it to there. And then down here, I would take my neutral. Huh? Oh, I'm sorry. Thank you. I don't need to take them all out. So I'd put a jumper down through there. And then what I would do is I would have my common running out here. And then what would I bring down here? I'd bring the neutral down here and hook it there. Right? And then my outputs would hook up here, 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 here. Is this syncing or sourcing? Neither. It's AC. Right? AC is, so what we do is we always, on AC, we use the neutral for our what? For our common, and then we use L1 for our output. Now, if I wanted to hook this thing up for sourcing, then what I would have to do is I would have to have an external DC power supply. Right? Oh, let's do syncing because that's what we got. So I have to have an external DC power supply. I'm trying to make room. This might be good enough. And then what would I do? What we want to do is we want sourcing input. So what I do is I take the positive
and run it here, and here, and here. I'm gonna stop, right? Then I would take my negative, and then I would hook this up to my output. Oh, not like that, Rich. Duh. I'm hooking up a series circuit, right? So my negative would come down here, and it would be the common for my output device. I'm still trying to do it. Y'all understand? But I could just as well come in here and do swap this around. Now our 1100s are set up to be they're AC. So that means if you look down at the actual switches, if we take it apart, you see the neutral jump into all the, not the switches, all the watts, all the loads. We're okay. So this is a our 1000, our 1100s. These are the 1100s. This is the 1000. I thought I had the 1000 first. Now this is the 1000. We looked at that. They show it. This is the 1100s. This is the S7. These are the 12, 14. This is the C jump. And this guy right here, you have no option.
You have what?
You have no option. Oh, I forgot to show y'all this. This is the 1100. These are analog, so it has two analog inputs. Set up an analog common, so this would be a 10 volt supply, right? And then this would be two analog inputs. And the 1200s have two analog inputs also. So that's these guys right here. These guys here are analog inputs.
I know they have a lot of this inside.
Huh?
Oh, I see.
Now this is analog. These are labeled A1, A, yeah. So these are analog inputs. And we have to have this guy right here generates its own power supply. So EMs, by the way, I'm sorry. This would be, these guys right here have to have their own power supply. So they're going to generate a voltage between what? 0 and 10 volts. And how you wire those up depends on the actual device itself. But notice I have no option here. So my common goes down through all my inputs. This is going to connect to EM. So the way Siemens is set up, L is what? Plus DC, M is minus DC. Okay, does that make sense? This guy here has an output that's EM. So I could have took this output, I could have took this output right here and connected it and used it instead of this right here. What they're doing here though is they're using an external power supply. Make sense? Is that okay? So here's where I powered up. I put 24 volts in right here. So this is a DC input. 24 volts right here. And then it gives me an output, which is what? 24 volts, right? And then what we would do is we could take this right here and we could run it and use it down here. So we can't use this power supply to power our output, right? So what we have to do on our output, we have to have a what? External power supply. So these inputs are hooked up what? Sourcing. The input devices are hooked up sourcing. So like these are automatically set up for what? These outputs, notice the positive goes up to 3L, so that's positive. And then my common comes down here. This establishes a common for your input, by the way. We can talk about that. And so these guys are hooked up what? These are sourcing, and then my loads are going to be what? And these are our 1200.
Notice the 1200s, go in groups of 8. It goes 0, 1, 2, 3, 4, 5, 6, 7, and it drops back to what? 0. So this would be the second 8-digit number. And then my inputs do the same thing. 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5. So this guy here's got 16 inputs, right? And it's got, 10 outputs. So what I would do, these would be addressed. These addresses are fixed into that. So my inputs,
Anybody know how they address? They go I, and they put the byte number. So this would be byte 0. And then they put a dot, and then they put the bit number. So that gets everybody confused. Because Allen Bradley, if I use a dot, it means a word. Yeah. So when I got to this group right here, it would be what? I 1.0. So this is a big difference between Allen Bradley. If I wanted to input a byte, I would go IB.0. If I wanted to input a word, you'd use what? IW, 0.0. We wouldn't specify bit. If I inputted byte, it would be IB0, right? So Allen Bradley and that's a little different. Now the RS Logic 5000, which is the next version of their of Allen Bradley's programming software. I don't know how they address inputs and outputs. I'd have to go. We have. In 504, and this is, I think this is the last slide, so we're finishing up perfectly. And I put this link in there. The 504, by the way, is pretty much well. I don't know if this link's gonna work, guys. But what I want to do is just show you all the modules that's available for the 504. It takes a while. So these are all the different modules you can, if I can get down to the modules. Input module for programmable controller. This doesn't tell you if it's syncing or sourcing, but you can get about module. They have analog modules. They have communication modules. They have all this that's available. Well, look at that. Huh? Yeah, and slot fillers, analog inputs. So this would be the analog inputs that's available. Number of channels. And then, but they all would just plug right into the wall, into the chassis. Okay, y'all that came in late, let's tell you what we're going to do. We're going to let y'all